Welcome. This video is going to look at more physical properties from Section 2, Chapter 3 from the Brown SL Chemistry book. So we talked about atomic radius just briefly in the first video. So ionic radius is just what it sounds like. It's the radius of an ion. And you can see the trends on this graph or on the chart pretty easily. If you look at the IB data booklet, they'll give you these radii. And you notice that there's generally a decrease as you go left to right, although all of a sudden when you hit the nonmetals, there's a big increase and then it starts to decrease again. And there's an increase as you go down, except when you go from nonmetals to metals, there's a big decrease and then it starts increasing again. So we seem to have definite trends going across and down the table as well as within the metals and nonmetals. So let's take a look at why. The 5 trends in ionic radius can be identified as, first of all, positive ions are smaller than the parent atom. That's because you lose the outer electron shell for it to become a positive ion and become a stable ion, and yet the net nuclear charge remains the same. So these two things are going to combine to give it quite a bit smaller radius. Negative ions, on the other hand, are going to be larger because the extra electron is going to increase repulsion even though the net nuclear charge remains the same. It is going to be quite a bit bigger than the parent atom. Number 3, the ionic radii decrease from groups 1 to 4 as you go across the metals because the positive ions are losing 1, then 2, then 3, and 4 electrons. So as you lose more and the nuclear charge gets stronger, we see a decrease in size just like we did with atomic radii. Ionic radii also decrease from groups 4 to 7 because the negative ions gain 4, then 3, then 2, then 1 electrons along with the increased nuclear charge. And then number 5, the positive ions are always smaller than the negative ions. Positive ions lose electrons, lose an outer shell, whereas negative ions are gaining, increasing the repulsion. So that's why we see this change in radii as you move from metals to nonmetals, or as you go down the groups from nonmetals to metals. So basically, ionic trends are very similar to atomic trends. We see a decrease as we go across a period, and the electron repulsion increases and the nuclear charge increases and no new energy levels. And we see a decrease as we go down and we add more energy levels, keeping the same net effective nuclear charge. So then the next property relates directly to size, and that's something called ionization energy. Ionization energy is the energy required to remove 1 mole of electrons from 1 mole of a gaseous atom. And this would be a 3-mark definition on an IB exam, so this would be a good one to know. First, ionization energy is really a measure of the attraction between the nucleus and the outer electrons, because the stronger that attraction, the more energy is needed, the higher the energy. So ionization energies will increase across a period as your atoms get smaller and the electrons get closer to the nucleus and they're held on to more tightly by that bigger nuclear charge. But ionization energy will decrease down a group because it has the same effective nuclear charge going down the group, but more energy levels. So you have electrons further away from an equally strong nucleus. So this is where I get the idea that lower left are large losers. Ionization energies can also be described as second, third, and fourth ionization energies. Generally, when we say ionization energy, we're talking about the first ionization energy, or the energy to take that first electron off. So second, third, and fourth are just what it sounds like. It's the energy to remove the second, third, or fourth electron, and it will always require more energy to take the next electron off. And part of the reason is because there's fewer electrons left in that energy level to help repel or push the electron out of the cloud. There's 3 situations in which ionization energies don't follow the trend so well. And that is when an energy level is emptied, the next electron removed requires a huge increase in energy. There's always an increase in energy, but we see this disproportionate or really big increase in energy when you move to an inner energy level and try and start removing electrons. Removing an electron from a p orbital instead of an s orbital. It's actually easier to remove an electron from a p orbital than an s orbital because the p orbitals generally are further out and easier to remove, so they're further away from the nucleus, easier to remove than from an s orbital. And finally, removing an electron from a paired p orbital versus an unpaired p orbital. Paired p orbitals, if there's only one paired p orbital like p4, when you first pair it up, the other two p orbitals are still unpaired. That p4, that one p orbital that's paired up, is happy to get rid of that extra one because there's always repulsion when you put two electrons within an orbital. So we see that here with aluminum. Aluminum has 13 electrons. So right here, when you go from electron 3 to 4, you move from the third energy level to the second energy level, and we see a pretty good increase. Now, that doesn't look so big, but when you look at how minuscule the increase had been when we removed the second and third electrons, that's a pretty good jump. And we see it here with the numbers, that it's, over 4 times as much or close to 4 times as much. And then we see, it's a little bit hard to see here, the trends with the p orbitals, but we see the other big increase right here when we go to that inner orbital between the 11th and 12th and try and remove those two in the s orbital. Here's an easier place to see the p and s orbitals I was talking about. So the first ionization energies for periods 1, 2, and 3 are shown. So here's hydrogen, lithium, sodium, and potassium as we move down a family. Actually, this is hydrogen, then sodium, then potassium as you go down. And you can see the ionization energies are decreasing as we go down family 1. As you go down family 2, you would have to start with lithium and work your way down. But you can see that it decreases down a family. And then as we go across, you see that from hydrogen to helium, there's a big increase. As we go from lithium to beryllium, there's an increase. So this would be S1 and then S2. But then when we start filling up the P1, it's actually easier to remove this electron than to go back and remove this electron. But then it increases for P2, P3. But now when we put P4 in there, P4 is easier to remove than P3 because it's unpaired. But then it increases for P5 and P6. And then we come back around to the next energy level, and it's going to take less than it did for lithium. And we'll see the same patterns repeat. The next topic to talk about, the next property, is this idea of electron affinity. And this is similar to electronegativity, but electron affinity means attraction to, so it's the energy change when 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of gaseous ions. So electronegativity is actually talking about covalently bonded pairs of electrons and how much it attracts to it. This would be how likely is an atom to accept an electron. And so obviously our nonmetals, especially families 5, 6, and 7, are going to be much more likely to accept those electrons than the metals, which are usually looking to get rid of an electron. And just like ionization energies, you can have a first, second, and third electron affinity. And this is usually an exothermic process where ionization energy is an endothermic process. So the first added electron is going to be attracted by the positive nucleus. So again, that's going to make it exothermic. It's going to release energy as that nucleus pulls in that new electron, that extra electron. So what are the patterns or trends in electron affinity? They're basically the opposite of what we see with ionization energies. Because ionization energy, if ionization energy is low, it's likely to lose an electron. If electron affinity is high, it's likely to gain the electron. So group 17 has the greatest affinity, or the minimum value. It's the largest negative value, so it releases the most energy. So it's most likely to gain electrons, which makes sense since they have a net effective nuclear charge of 7. It's got the strongest nucleus, plus they're the smallest. They're the closest to the neighbor's electrons. Group 1 has low affinity with a net effective charge of 1. Another trend or pattern to point out is that affinities actually reach a maximum value, or atoms with the least amount of affinity are actually in groups 2 and 15. And again, this is because group 2 will need to pick up that extra electron and put it in a p orbital, which is further out. So it actually requires energy to put it out there and hold it. And group 15 has all 3 p orbitals with 1 electron. So it's actually a little harder for group 15 to gain that electron than it is for the other nonmetal groups. Just a couple quirks in electron affinity. So electronegativity is the one we tend to focus more on. It's similar to electron affinity, but this refers to the atom's ability to actually attract the covalently bonded pair of electrons. And this is where the whole idea of polarity comes in. So electronegativity is defined as the measure of attraction for a shared pair of electrons. So it has to be a pair of electrons in a covalent bond. Higher electronegativity is going to mean stronger pulling power, while lower electronegativity is going to mean weaker pulling power. So these trends are actually going to be the same as ionization energy. If something has a high electronegativity and is able to pull on that pair of electrons, then it's also going to have a high ionization energy and be unlikely to lose electrons. So we're going to see electronegativity increase across a period because the increased nuclear charge is going to mean the nucleus is closer to those bonding electrons and it's stronger. But we're going to see a decrease down a group because the bonding electrons are going to be further from the nucleus and there's not going to be any increase in nuclear charge. So there's actually going to be a decrease in attraction. Fluorine is the most electronegative element. It's given a rating of 3.98 or 4 on some scales. And cesium is the least at 7. Really, francium is the least electronegative, but it often isn't even assigned a value because it's so rare and unavailable for reactions. But there's really no units with these because this is just a scale devised by Paulin. It's just in comparison to other elements, how electronegative is it. And again, the trends are similar to ionization energies, but they are different properties because ionization energy is a property of a gaseous atom, and we can measure it directly, how much energy we have to put in to remove that electron. Electronegativity is a property of an atom in a molecule, so values have to be derived indirectly from experimental data. But in general, metals will have low ionization energies and low electronegativities, making them large losers in the lower left, and nonmetals are going to tend to be small and tight in the high right corner, making them more likely to gain electrons. The metals also have this freedom of movement with their delocalized electrons, which give them that conductivity we'll talk about later. So the last thing to try and talk about quickly here, the last physical property that's often used to explain chemical behavior is melting point. And melting point is going to depend on the type of bond and the structure of the element. Now bonding, because these are metals, is either going to be metallic for the metals or it's going to be covalent for the nonmetals, because remember, we're still talking about elements here, not compounds. So metallic bonds is when a pure metal bonds only to itself. It's this idea of the sea of electrons, the nuclei, positive nuclei line up like cations, but the electrons are just kind of shared out there or pooled and are free to move. So more outer electrons will increase the strength, whereas more energy levels will decrease the strength. So we see a similar trend here that the melting point across a period will increase for metals, but it will decrease as you go down the family for metals. The nonmetals have just the opposite going on because nonmetals bond covalently to themselves and form a nonpolar or pure covalent bond. So that means the only thing holding them together are these weak London forces or dispersion forces. So more total electrons, whether they're inner or outer electrons, just more total electrons will increase the overall attraction, make it more likely that a dispersion force, temporary dipole, occurs. So we're going to see melting point increasing down a family for nonmetals. Within the family, it gets a little bit goofy. Metallic bonds are generally stronger than covalent bonds, so moving across a period, the melting point will increase across the metals, and most of the metals will have a higher melting point than the nonmetals. The one exception is when we get to group 4. Group 4 is unique because it can form 4 different bonds, covalent, ionic, whatever, but 4 bonds. So with group 4, carbon and silicon, they are able to form these giant covalent bonds, or what we call network solids, and these giant covalent bonds, think of diamonds, have a higher melting point than even any of the metals. So we see an increase across groups 1, 2, and 3, and even an increase with group 4 when we hit those nonmetals. But then as soon as we get past group 4, the other nonmetals are forming weak covalent bonds. They either have a triple, double, or single bond, nitrogen triple, oxygen double, chlorine single bond. So now the melting point starts plummeting, and it's actually quite a bit lower than it was for any of the metals, even the group 1A metals. And then finally you get to group 18 with the noble gases, and they just exist as atoms. They're called gases because their melting points are so ridiculously low, so melting point drops even further. So this slide kind of shows you the trend as you go across a family. So if you start with lithium, It's going to increase to beryllium, boron, and increase even more. So these are metals that we're seeing the increase in. This is our giant covalent structure, which has the highest melting point. And then they just plummet. You notice nitrogen, oxygen, and fluorine, not a huge decrease there, but quite a bit less than it was even for the first metal. And then neon, even a bigger drop. And then we see the same pattern repeat as we move to the next family. Now with aluminum, we see a little blip there, and that has to do with it being a metalloid. Sulfur, we see a little blip, and that has to do with the fact that sulfur tends to form as S8, whereas phosphorus tends to form as P4. But in general, that's the pattern. It rises across to group 4 and then plummets through the nonmetals.